Hello everybody, I'm back. So in this video I want to talk about a another first order partial differential equation with constant coefficients. So suppose we have a partial of u partial of x plus b partial of u partial of y equals 0. So in this video we're going to deal with the right side being 0, so this PDE is said to be homogeneous. So the way to solve this for u is to interpret the left side as a dot product of two vectors. One is going to be a comma b, and the other is going to be of the partial derivatives of u. So this vector on the right here is known as the gradient vector. And this vector here is a direction vector. I'm going to call it d. Now, this equation here indicates that u does not change in the direction of d. Therefore, u changes in the direction orthogonal to d. So we can write u, xy, is an arbitrary function in the direction perpendicular to d. So this here will be the general solution to the PDE we started with. Oh, and of course, I should mention, u is a two-dimensional function of xy. We'll get into the three dimensions. We'll get into the case of three dimensions later. So for now, this is the general solution. I'm going to illustrate this better with an example. So let's say we have partial of u partial of x plus 2 partial of u partial of y equals 0. So as before, this is going to be 1 comma 2 partial derivatives of u equals 0. And so now this here is 1 comma 2 dot gradient u equals 0. So now what I do is I'm going to draw this vector in the xy plane. So u is a two-dimensional function. So this here is going to be the xy plane. And let's see, the rise is 2 and the run is 1. So it's going to look like this. So this here is 1, 2. And if you remember from elementary algebra, the way to get the perpendicular slope is to take the negative reciprocal. So if this slope here is 2, then this here is going to have slope m equals negative 1/2. So in this case, the rise is negative 1 and the run is 2. So this vector here is going to be 2 comma negative 1. So, oh, and I should mention that this is not the only vector you can use. Obviously, this vector is also orthogonal to 1, 2, and this will, you could use this one and you would have a perfectly legitimate general solution, but I'm going to work with 2 comma negative 1. So I'm going to say that u, xy, equals arbitrary function of 2 comma negative 1 dotted into x, which is xy. Oh, and I should mention that when I said x before, x is a position vector. So because we're working with two variables here, x and y, in this case it's going to be the vector x comma y. So if I do the dot product, I get f2x minus y. So this is the general solution to this PDE here, and I can check it by taking derivatives. So partial v partial of x it's going to be f prime and then times the derivative of what's inside with respect to x. So y is treated as a constant, and I just get 2. And now partial of u partial of y, this is f prime times the derivative of what's inside with respect to y, so it's going to be -1. And now if I plug in these two formulas here into the PDE, I get 2f prime for the first term, and then plus 2 times -f prime. And yeah, 2f prime minus 2f prime is 0, so this here is the general solution. So as I said before, if we could also use this vector here, it would be -2, 1, and it would give you f of -2x plus y, and that would also be a perfectly legitimate answer because f is arbitrary. So what I'm going to do now is talk about the three-dimensional case. So let's say that we have this PDE here. So here u is a three-dimensional function of x, y, and z. So, as before, I write the left side as a dot product of two vectors, a, b, and c, as well, and the second vector is going to be of the partial derivatives of u. So, alright, so this vector on the left is going to be my direction vector, and the vector on the right is going to be the gradient vector. So, as I'm going to say it again, this equation here on the bottom indicates that u does not change in the direction of d, and therefore u must change in the direction perpendicular to d. So arbitrary function of, so because we're working in 3 dimensions, if I have a vector that points in some direction, there's going to be a whole plane perpendicular to that vector. So I can choose any two linearly independent vectors within that plane as my d perpendicular 1 dot x and d perpendicular 2 dot x. So I think it's best to illustrate this with an example. But as before, in the two-dimensional case, I could choose between two perpendicular vectors that are orthogonal to the 1, 2 vector. In this case, I can choose any two vectors in a plane. So there's a lot of freedom, and the reason we can do that is because f is arbitrary. So let's illustrate this with an example, shall we? Alright, so I'm actually going to deal with the same equation plus 2 partial of u partial of y equals 0, but now u is a three-dimensional function. So because it's three-dimensional, I'm going to add plus 0 partial of u partial of z. So that way I can write this as 1, 2, 0 dot partial of u partial of x, and so on. So this here is going to be my direction vector 1, 2, 0. So yeah, now to find out what u is, I have to draw this vector here in the xyz in xyz space. So this here is going to be my coordinate system. So this here is x and y. So the direction vector 1, 2, 0 is going to look like this. So and one of the perpendicular vectors we found in the previous example, so it's going to be in the xy plane with slope -1/2. So this here will be 2, -1, 0. So now we need a third vector that's perpendicular to 1, 2, 0, and we can choose the one along the z-axis, the unit vector. So it's going to be 0, 0, 1. So if we wanted to, we could choose these two perpendicular vectors, but that's just making it more complicated. I'm just choosing 2, -1, 0, and 0, 0, 1 for simplicity. So the general solution for u, x, y, z equals arbitrary function of, the first one is 2, -1, 0, dotted into x, y, z. And the second perpendicular vector is 0, 0, 1, so dotted into x, y, z. And now if I evaluate the dot products, I get 2x minus y, comma, z. So this is my general solution for this PDE here. And I should mention that even though f is a two-dimensional function, u is a three-dimensional function because it's of x, y, and z. So yeah, don't be fooled. U is a three-dimensional function, and it lives in four-dimensional x, y, z, u space. So how do we know that this is the solution? Well, we can check that it is. So I'm going to start by, I'm going to take derivatives of this. So partial v partial of x is going to be, so if this first argument here is x and the second one is y, multiply that by the derivative of what's inside the first argument with respect to x. So times 2. And now partial of u, partial of y. Oh, whoops. I need to finish. So yeah, for du dx, I took the derivative of the first argument with respect to x, so that's this first term right here. And now plus derivative of the second argument with respect to x of z. So z is an independent variable, so taking the derivative with respect to x is going to be 0. So that's why I just ignored the second term here. So it's just 0, so no need to worry about that. If I take the derivative of u now with respect to y for of the first argument, df dx, so with respect to y, the derivative is going to be -1. So -1. And now for the second argument, df dy, times the derivative with respect to y of z. So as I said before, z is just an independent variable, which is not y, so the second term here is going to be 0. Alright, so I'm going to plug in these formulas now into the PDE. So for partial of u, partial of x, it's going to be 2 df dx, and then plus 2 times du du dy, so that's negative partial of f partial x. And 0 is just goes away, right? So this here is going to be 0. So this is the correct solution. Alright, so before I end this video, I want to do one last example. And that is if u satisfies two PDEs. So let's say that I have partial of u partial of x plus 2 partial of u partial of y plus 3 partial of u partial of z equals 0. And u also satisfies 2 partial of u partial of x plus 3 partial of u partial of y plus 4 partial of u partial of z equals 0. And u is a three-dimensional function of x, y, and z. So I want to know what function satisfies these two PDEs here. So what I do is I write the left sides as a dot product. So 1, 2, 3, dotted with the gradient vector equals 0, and 2, 3, 4 dotted into the gradient vector equals 0. So this equation here indicates that u doesn't change in the direction of 1, 2, 3, and this equation here indicates that u doesn't change in the direction of 2, 3, 4. Therefore, u must vary in the direction perpendicular to both 1, 2, 3 and 2, 3, 4. And what vector is that? It's going to be the cross product. That's going to be the direction vector, that the perpendicular direction vector that we want to use. So we say that u x, y, z equals arbitrary function, or I should use square brackets here. So this is going to be, never mind, just parentheses. Okay, so this is going to be 1, 2, 3 cross 2, 3, 4 actually, never mind. Changed my mind again. So, and then dotted with the position vector x. So yeah, because u is a three-dimensional function here, x, the position vector is going to be x, y, z. So very quickly now I'm going to do this cross product here. So I have x hat, y hat, z hat, and 1, 2, 3, 2, 3, 4. So let's see what this is. So x hat, and then this is 8 minus 9, so negative 1, minus y hat. This is 4 minus 6, so negative 2. And now plus z hat, that is 3 minus 4, so negative 1. Alright, so I can say now that u, x, y, z equals arbitrary function of, let's see, this is negative 1, comma 2, comma negative 1, dotted into x, y, z. And this is equal to negative f negative x plus 2y minus z. So this here is the general solution that satisfies both of these PDEs here. And we can check it. So I'm going to start by taking the derivatives now. So let's see, partial of u partial of y. I'm sorry, I'm going to start with x. So partial of x equals f prime times the derivative of what's inside with respect to x, so that's going to be negative 1. Now partial of u partial of y, this is f prime times derivative of what's inside with respect to y, so that's just 2. And finally, with respect to z, what do I have here? I have f prime times negative 1. So if I plug in these formulas here into the PDE, I get, for this first PDE, I get negative f prime, and then plus 2 times 2f prime, so that's 4f prime, and then plus, or actually no, it's going to be minus now because of this negative 1, so minus 3f prime. And this does indeed add up to 0, so this first PDE is satisfied. Now I'm going to plug in these formulas here into the second PDE. So let's see, this here is going to be negative 2f prime for the first term, and now plus 6, because 3 times 2, so 6f prime, and then minus 4f prime. So yeah, this does add up to 0, so this is the correct solution. Alright everyone, thank you for watching. I'll hopefully see you soon with another video. Take care.